Welcome everybody. I'm Kit Neal. I'm the backup moderator here. The main one I think is having some trouble. And our presenter is Dr. Syal, and I'm not sure if she can push her slides yet. So hopefully she'll send me something. Oh, there's Minta. Once you connect to audio, I'll turn it over to you, Minta. I think we're waiting on Megan to work out something and push the slides. I'm sorry, everybody. APS was a little late in opening up the meeting, and so we're all kind of running behind on getting things set up. Do you want to take over, Minta?
Sure. I couldn't get my other microphone to work, so can you confirm you can hear me?
Yeah, I can hear you, and they say that we are live. Apparently, there are about 50 people listening to us debug.
Yeah, that's always the best, isn't it?
That's right. That's right. So, okay, well, I will mute myself and turn it over to you now that you've connected.
Okay, so just as a reminder for everybody, the important message is that you need to vote. Please vote for your future XCOM members and chair. The link should have been emailed to you, and it's down at the bottom. There's also a new unit website up. So hopefully that will be a forum for people to interact. Please give us feedback. Let us know what you think of it. Today, Megan Syal was going to speak on planetary defense. In January, our plan is to have two speakers, Kit, who was just on, and Christopher Molick. And so that'll give you a very different sample compared to what you'll see today. And then in February, Marcus Knudsen will talk about shock physics happening at Z. So that should cover everything. Dan, can you remind everybody, the idea here is that I will read any questions out so that not everyone can see the chats. But Dan, if you can remind people how to send the questions to Kit and to me so we get everything nice and clear, that would be great.
Yeah, you should be able to see a Q&A button at the bottom of your Zoom window. Just use that to submit your questions. The chat will remain off.
Okay. And Megan, you want to test your audio real quick? Let's make sure it's working.
Yeah, can you hear me?
Yes, I can. That's great.
Yay. Great.
We got there in the end.
Yeah.
So Megan is a physicist here at Livermore. Her specialty is the Planetary Defense group. She has a doctorate in geology from Brown, as well as the usual litany of undergraduate degrees. And today she's going to talk to us about planetary defense and some of the efforts going on here and around the country in that area. Megan, over to you.
Great. Thank you, Minta. So I'll begin with some background on the nature of the threat of asteroids. And this plot is showing asteroid diameter on the x-axis versus the number of asteroids that are known or expected to be out there. So the observed asteroids are shown in the blue curve, and the asteroids that we think are out there based on redetection rates and also simulations of the population are shown in the black dots. And what you can see is that the larger size ranges, things a kilometer or larger, more than 95% of those are well characterized, and they're also known not to be threats to the Earth anytime soon. So that's very good news. The dinosaur killing asteroid called Chicxulub from 65 million years ago, that was 10 kilometers in diameter. There's nothing like that we're worried about in the near future. The only thing that could be that size and be a threat anytime soon would be something like a long period comet that came out of the outer solar system. But as I alluded to in my abstract, Chelyabinsk, which was an asteroid that exploded over Siberia in 2013, really called the world's attention to this problem. It was relatively small. That was 17 meters in diameter, but it deposited 500 kilotons and blew out a lot of windows, injured a lot of people. Thankfully, no one was injured. And you can see at that size range, there's hundreds of thousands of asteroids that we don't know where they are. So we really need space-based observatories that are fully dedicated to hunting down asteroids in those tens to hundreds of meters size range. If you go just a little bit bigger than Chelyabinsk, Tunguska was 60 or 70 meters in diameter, rocky asteroid. It exploded over Siberia in 1908, and it flattened 2,000 square kilometers of forest. That's shown in the bottom right there, a photograph of what that looked like. Thankfully, that was not an inhabited area. If it occurred over an urban area, that's roughly the size of the Washington, D.C. metro area. So that would be very devastating today. And so that's what's really alarming in some ways, that there's so many asteroids that size that are out there right now that we don't know when or if they're going to impact the Earth. And so there's a lot of work that needs to be done on the detection front. But then what we work on more in our group at the lab is if it is detected ahead of time, what we could do about it. There's also a picture here of Meteor Crater in northern Arizona. A great field trip. I highly recommend stopping by if you have a chance. It's halfway between Flagstaff and Winslow. It's over 1 kilometer in diameter, and that was created by something that was only 50 meters in diameter, an iron nickel asteroid, so higher density and especially dangerous. The National Near-Earth Object Preparedness Strategy and Action Plan came out of the White House's Office of Science and Technology Policy a couple of years ago. A lot of experts contributed to that, including some from the national labs, to really provide a roadmap for the next 10 years of how all the federal agencies and departments could work collaboratively to make sure that our country is more prepared for a real emergency if one comes along. And we contribute to several of these areas, but the main 5 goals can be summarized as enhancing NEO detection, tracking, and characterization, so more fully dedicated telescopes. An example of that is the Near-Earth Object Surveillance Mission, or NEOSM, which will hopefully launch in the next few years. It's based out of University of Arizona. Amy Meinzer is the PI on that, and I'm really hopeful that will get off the ground soon. An area that we contribute a lot to in our group is the improving of near-Earth object modeling and prediction and information integration. So a lot of hydrocode simulations to better understand asteroid response to various mitigation techniques. Developing technologies for NEO deflection and disruption missions. The best upcoming example of that is the Double Asteroid Redirection Test, or DART, which is scheduled for launch from Vandenberg this coming summer. And it will be the first ever deflection test at a real asteroid. Really incredible opportunity to test our ability to model those impacts and see how effective they can be to deflect an asteroid. And then increasing international cooperation on NEO preparation. It's a very global problem, and the spacefaring nations like the United States bear a special responsibility to be better prepared, be ready to act, and able to help if there's an emergency. But we have these planetary defense conferences every 2 years where there's very global participation. The next one in April will be 100% virtual, which hopefully will enable even more global participation. And finally, strengthening and exercising NEO exercise impact, NEO exercise and impact emergencies, our protocols and our action plans for these scenarios. We do that regularly at the Planetary Defense conferences. We also have tabletop exercises with FEMA and NASA with the other NSA labs. And so that's a really important part of being ready. And if an asteroid were going to impact the Earth, there's a few different mitigation options available. We model all of these, The first is if there's not a lot of warning time, we can do consequence assessment for emergency response. So even if you're not able to prevent the impact, you can at least advise on what kind of evacuation plans should take place and what kind of critical infrastructure should be secured. So an example of this is the Sea of Japan impact shown here. This is some work by Syal and showing how water waves are generated over long distances and what kind of flooding results. You can also do a handoff to a global circulation model to see the injection of chlorine, for example, into the atmosphere that can have long-term effects on the ozone layer. What does that mean for our climate over longer time scales? If we have a little bit more warning time, we can stage a deflection, which means that you deliver some momentum impulse to the asteroid. The bulk of it stays together, and its velocity is changing only by a little bit. So the typical figure of merit is A centimeter per second change in velocity for 10 years of warning time is typically sufficient for most orbits. It depends on the details of the asteroid's orbit. And the two main ways that we model to achieve this are a kinetic impactor, which is just crashing a spacecraft into the asteroid at tens of kilometers per second, typically, which delivers a lot of momentum, but you get a momentum boost from any ejecta that's produced by the cratering event. And then in other scenarios where kinetic impact is not sufficient, we also model standoff nuclear explosions to deflect the asteroids. Again, you're keeping the bulk of the asteroid together in one piece. You're just blowing off material from the surface of the asteroid, which gives it a little bit of delta V in the opposite direction. And finally, if we need to stage something very short warning time, we can do a disruption. So robust fragmentation and dispersal of the asteroid, where a very strong shock wave rips through the asteroid, produces a lot of fragments. And this is a two-stage calculation. The hydrocode calculation to see what kind of fragment distribution is produced, and then an n-body gravity calculation to see how those fragments evolve over time and to make sure that they all safely would miss the Earth. A little bit more on consequence assessment modeling, specifically ocean impacts. This is work by Syal, who's our resident expert on this topic. The bottom left, you can see that the calculation begins with a hydrocode simulation, which creates our source term for the water wave propagation. So something like the geodyne hydrocode shown here. There's a lot of energy going into vaporization of water and other things. And then you're handing off to some other code that can handle elastic wave propagation over much longer time scales and length scales. So in this case, this is from a Planetary Defense conference that took place in Tokyo. And so the asteroid impact was also going, that was the scenario study for that particular conference, was also going to occur near Tokyo. And in this case, early on, you don't know exactly where it'll impact. The risk corridor could be very long, extending over thousands of kilometers. So it might impact China, it might impact the Sea of Japan or Japan. Here, if it's going to impact in the Sea of Japan, Syal's including all of the detailed bathymetry, the underwater topography, to show how those waves will propagate. So that's shown in the far right. The blue and red are showing negative and positive wave amplitudes over several hours. And then the final stage, which I don't show here, is Syal maps out all the detailed inundation zones in Google Earth in different cities. And so this is really important for being able to advise emergency response. And more recently, we've expanded our hydrocode modeling of ocean impacts into another code, AL3D. And Betsy Seifert has done a tremendous amount of work on this, and she put together some of these videos I'm going to show. On the left, we have the pressure field, on the right, a density field. And we begin with pretty high resolution near the impact site using adaptive mesh refinement. This is really important for resolving all the details of the energy partitioning from the asteroid to the ocean and the atmosphere. And then as you get to longer time scales, you remap to a little bit coarser mesh. And this is going from, let's see, there it is, the little bit coarser mesh. You can also see on the left side that there's a gradient in the ocean pressures, and that's because it's in hydrostatic equilibrium. And at about 3 kilometers depth, it reflects off the ocean floor. And that pressure wave is pretty low amplitude. That's something like half a kilobar or something, but really interesting to get the full context of what this event looks like. And then remapping again to a little bit coarser mesh and going over longer time scales out over to 3 seconds. This provides confidence that by the time it's handed off to the next stage of the calculation, whether that's a global circulation model to monitor the injection of chlorine into the atmosphere or other volatiles into the atmosphere and seeing what that does to our climate, or handing off to an elastic wave propagation code like SWWP to see what kind of flooding occurs, that this portion of the cratering process is complete. And another aspect of consequence assessment is being able to model these airbursts really well. So events like Chelyabinsk and Tunguska, most of the energy is being deposited in the atmosphere. And the details of that asteroid breakup and explosion are really interesting to model. A lot of the previous work on this has been using reduced order models like the pancake model or the fragment cloud model, which are used to predict airburst consequences. And Jason Pearl, who's a postdoc in our group, has done a lot of work recently with Cody Raskin and Mike Owen using the adaptive smooth particle hydrodynamics code Spheral to more fully model this atmospheric entry and breakup process. So not using the reduced order models. This is really important because the details turn out to really matter. Things like the asteroid's porosity, its shape, its strength, including all of that affects the details of how it will break up in the atmosphere. And so ideally, you don't want to have to be making assumptions about how it's going to be depositing its energy. You want to be able to model all of that in detail and in 3D, ideally, because most impacts are coming in at some impact angle. They don't come in at 90 degrees. The average impact angle is 45 degrees. So we need to be able to model all these different initial conditions. This particular example was one that was part of a code comparison effort with the modeling working group, one of the groups that was spun up in response to the Near Earth Object Preparedness Strategy and Action Plan. So we do a lot of work comparing with our NASA collaborators, other DOE labs. And this is an example, something coming in at 45 degrees, about 3 million ASPH particles, 720 CPU over 10 hours. So this is kind of medium-sized calculation, and sometimes even much larger calculations are needed for these kinds of studies, but really interesting work. Now moving over to deflection, if we want to model kinetic impactors correctly, it often requires 3D modeling, because if you take a look at a real asteroid like Itokawa on the top right here, you see that they have very varied shapes. They're very 3D. Depending on what angle what direction you're coming in from, your impact angle can change quite a bit. The local topography can control a lot of what's happening with the details of the cratering process and what the ejecta field looks like. And I'll play this movie here of an example of an ellipsoid representation of the DART target, which is called Dimorphos is the name of this small asteroid, about 150 meters across. So here the impactor's coming in from the right side and it's coming in slightly off axis. Now, in a real mission, your AutoNav software is targeting the center of figure best as it can, but any asteroid is going to have some variability in its shape and structure, and you're not necessarily going to get super lucky and come in right around 90-degree impact incidence. So it's important to understand how the ejecta will change depending on the impact angle. And in this example, all the ejecta that's colored here is going to the right and contributing to our total momentum delivery to the asteroid. But ejecta that's gray, it's going in the wrong direction for us. So it's going to the left, which is actually counterproductive for the direction that we're trying to push the asteroid. So it's important to understand how that momentum delivery degrades with impact angle, because the conditions are not going to be optimal in a real deflection scenario. And another thing I should mention, you can see with the Itokawa image, is that the structures of asteroids are very have a lot of heterogeneity in them. So we typically refer to these as rubble pile structures. They're very collisionally processed. They've experienced a lot of impacts over their lifetimes. And so it's a kind of a grab bag of different boulders of various sizes and some finer grained material mixed in. So there's both macro and micro porosity. It's important to model those details. And we also use radar derived shape models like the bottom right for Golevka. These come from radar observatories like Arecibo Observatory, which was very sadly in the news this week because of its collapse. And that had an unparalleled ability to get really detailed shape models like this on near Earth asteroids. So there's definitely a capability gap with Arecibo being out of commission at this point, but we look to those radar-derived shape models to understand more realistic depictions of asteroids. And an upcoming opportunity to test a real deflection is the DART mission. NASA's DART mission is going to launch this summer from Vandenberg in July 2021. And our team at Livermore has been helping out the DART team since about 2015 with predictive simulations of what we think will happen when this spacecraft impacts this little moonlet. And it's what's really interesting about this experiment is that it's a binary asteroid. So there's one larger one that's about 800 meters across. That's called Dimorphos. And then a smaller one recently got a new name. It's called Dimorphos, 150 meters across. So it's orbiting the smaller one's orbiting this larger 800 meter primary. And the spacecraft will impact the smaller one, and it will deflect it by a little bit, not too much. So here's a video of we're showing here what this will look like. Now the change in velocity to Dimorphos will be pretty subtle, something like a millimeter per second. But the fact that it's in a binary system means that the orbital period will change. And so it can be observable from ground-based telescopes, which is really key because we won't have another spacecraft, full-size spacecraft observing the whole event up close. We have to depend on ground-based telescopes to interpret how effective that deflection was. Now there's Didymos. We used to call the little one Diddy Moon. That was its nickname until it got a real name very recently, Dimorphos. So DART's going to come on in at about 6 kilometers per second. It's about 400 kilograms of mass. That's enough to deflect it by about a millimeter per second. It'll change its period very slightly, and we'll be able to observe that from Earth and back out how effective we think that deflection was, how much ejecta was produced by the cratering event. And so a lot of the work we've been doing over the last several years has been really focused on understanding these uncertainties associated with that event. Mike Owen has done a tremendous amount of work to support the DART mission. One of the most interesting things that he's added into Spiral has been new node generators that can produce a more realistic rubble pile type structure. So using a power law distribution of boulders, each of which have been perturbed with spherical harmonics, so they have a realistic stochastic variation of shape. And then you can fill in a given shape model like Itakawa on the bottom left, or on the right side here, we have just a idealized ellipsoid. Fill it in with those boulders. You can start with the bigger ones near the center or the smaller ones near the center, depending on your favorite model of boulder evolution. Folks have different ideas about how that might look in reality. And then fill in the interstitial spaces with a matrix material. So this allows you to have both micro and macro porosity modeled in your simulations and provide a much more realistic heterogeneous model for what an asteroid structure would look like. And another thing that turns out to be really important in some ways is modeling the detailed spacecraft geometry. So on the right, if you can see zoomed in that image, there's a little representation of the DART spacecraft. So that's using the real CAD model geometry of that DART spacecraft. And it's using solar electric propulsion. So it has two really big solar panels, which they're fairly, while they're large, they're fairly thin. And so some folks assumed, well, we probably can ignore that. It's not going to provide that much of an effect. But it turns out it really does change the evolution of the crater and the shape of the crater quite a bit. And in some cases could affect the momentum delivery to the asteroid to model all those detailed shape aspects of the spacecraft. So, and you can also see from that image that it's a very challenging computational problem to get all the high resolution details near the impact site and then still model the entire asteroid. So here we're modeling the entire asteroid, 150 meters across. So you need a smart way to ratio your resolution away from the impact site. And Mike's done a lot of work to make that work really well. You might have seen in the news this week that the Hayabusa 2 mission returned a capsule to Earth from asteroid Ryugu. So Hayabusa 2 was a follow-on to Hayabusa 10 years ago that returned samples from asteroid Itokawa, which we saw an image of earlier in the talk. Hayabusa 2 visited Ryugu, which is a different kind of asteroid, really interesting, had an incredible variety of experiments on board, and one of those was the SCI impactor, which is a little explosively formed projectile, or EFP, that they fired at Ryugu back in April of last year, or April 2019. And you can see in these images, if you zoom in, that the crater that it made, there's also images of the crater that have been published later, but these initial images are showing just some of the ejecta cone. You can see that it's very 3D, that there's more mass on the right side of that ejecta cone. And so modeling things in 3D is really important. And it turns out in this case, we think that there was a lot of boulders nearby that were affecting the evolution of that crater. But what Kirsten Halley did at the lab is she modeled the details of that EFP formation in AL3D. That's shown in the middle here. And that she's also worked with a summer student, Timmy Chang, more recently to expand this study even further. And Tane Remington has also helped out with this work, and they're doing a lot of the initial modeling in AL3D of the EFP itself, and then looking at using Spheral with some of these more sophisticated rubble pile generators and boulder structures to incorporate what we think the topography really looked like at Ryugu near the impact site, and be able to interpret the results from that cratering experiment. And that's really important to have this, it was only 2 kilometers per second, this particular EFP, so not super fast, but it's still a really interesting piece of data to benchmark our codes off of. And as I mentioned earlier, in some scenarios, you need to use a nuclear device if you want to prevent an asteroid impact. You can always opt to take the hit if you prefer not to use that, but if you want to prevent it from impacting Earth, there are some limiting factors for kinetic impactors. So launch vehicle mass is one. Above a certain, for any given asteroid, there's a limit to how much mass we can deliver with a given rocket. And so right now, using SLS, which isn't even quite available yet, even assuming we can use an SLS rocket, there's only so many of those that would be available and that we could even bring to an asteroid. Even if you want to do multiple SLS launches, there's a limit to how much mass you can get to a given asteroid. And so above a certain size, it won't be effective. And also below a certain warning time, it won't be effective. The other limiting factor is if the needed delta V exceeds the asteroid's escape velocity. So if you need to push on it so hard that you would begin to disrupt it, then you would have a weak disruption, which would create a fragment cloud that's poorly dispersed, which could be worse than the initial condition. So standoff nuclear explosion, where you're using an explosion some distance off the surface of the asteroid and depositing a lot of X-rays into the uppermost surface layers, vaporizing material. This can be used to deflect up to kilometer-class asteroids, and it can also be used to stage a disruption when necessary. So when there's a short warning time and you need to disrupt it into many fragments and to disperse those fragments very effectively. What's nice about nuclear deflection is it's a very tunable approach. So I'm showing schematically here with the asteroid Bennu shape model. If you back off to different standoff distances, you can decrease the X-ray fluence at the surface of the asteroid and impart a gentler push to it, depending what kind of push you need. And that will depend on how much warning time you have, how big the asteroid is, and its orbit. And here we're assuming that it's a 2 keV black body spectrum and 65% of the energy is re-radiated. And the details of re-radiation are really important, and important to capture that using a fully coupled rad hydro simulation. So Some of most recent really important work that's been going on in our group is to improve our X-ray energy deposition calculations. And that's really in the past, well, I should say, first of all, that mercury or MCMP plus a hydrocode is an approach that works well for neutrons, for example. And that's been used a little bit for X-rays in the past, but X-rays are more challenging because the re-radiation is significant. You want to be using really good opacity values for all of your materials, and you really need a fully coupled rad hydrocode to get an accurate estimate of how much energy is going to be re-radiated. And so what we've been using more recently is coal, which is a rad hydrocode, and using its implicit Monte Carlo transport. And that's really helping our understanding of re-radiation and X-ray energy deposition for a range of X-ray fluences and different asteroid types. So on the top left plot, that's showing some different asteroid compositions. Now that's using some of the older mercury depositions, which they do look a little different when you use a fully coupled rad hydrocode. And what we're in the middle of now is developing scaling based on incidence angle, target density, composition, influence. And so the idea is that any of these energy deposition curves then could be used in any hydrocode, whatever your favorite hydrocode is. And so the bottom left plot here is showing some of the newer coal depositions for different fluences. And because there's more complicated physics in it, it's a little bit harder to parameterize simply these energy deposition functions. So there's a lot of work going into that right now. But Mary Berkey, Nick Gentili, Kirsten Howley, and Rod Manigan have all been working a lot on this problem and made a lot of progress over the last year. And here's an example of disruption. If we needed to stage a disruption, here again, you're sourcing in a lot of energy to the asteroid, in this case, a megaton. And this is a pretty small asteroid. This is, I think, 100-meter diameter using a megaton close in, so a few meters off the surface. And we're modeling up to about 1/10 of a second here. And we model a little bit past this point before we then hand off. We make sure that the fragment field is done evolving before we hand it off to N-body gravity code that can then follow the evolution of the fragments over a longer time scale. So make sure they're well dispersed and they wouldn't pose any threat to Earth. And so clearly a lot of those fragments will be small enough that they would burn up in Earth's atmosphere. Some of them might end up being a little bit above that threshold, and that's okay as long as they have been moved into an orbit where they're not going to be a threat. So our research is driven by both our understanding of the initial conditions at the asteroid, but also the accuracy of our modeling. So I've talked a lot about how the asteroid initial conditions affect things, the porosity, the shape, the structure, whether it's rubble pile or more homogeneous. Rotation is another thing we've looked at in the past. The orbit is really important, and this is something we get to practice at the Planetary Defense conferences, how that risk corridor evolves with our understanding of where the asteroid is exactly. That was another thing that Arecibo Observatory was really good at, was pinpointing exactly where an asteroid was, and that helps you pin down whether it's going to impact Earth in the future or not, and then if it did, where exactly it would impact. But early on in discovery, as you can see in this example plot, which is showing in colors how many people would be affected by an impact, you might not know if it's going to impact over China or the Sea of Japan or Japan. And so that can really change how policymakers decide to deal with things. But another aspect, of course, is uncertainty in our modeling methodology. So making sure that we are doing resolution studies, that we're doing code comparisons, and also that we're benchmarking against real experiments is really essential. So DART is a very rare opportunity to benchmark against a full-scale experiment at a real asteroid using asteroidal materials. But folks in our group also do a lot of benchmarking against experiments on Earth. So Tane Remington has recently published a paper looking at benchmarking our fragmentation models against basalt spheres. These are experiments done in the 90s in Japan. So I'll play this video here showing what that fragmentation process looks like and what the ejective field looks like initially. You can see that's this impactor. It's a nylon impactor coming in at a few kilometers per second. And it's producing a bunch of fragments that are plotted on the right there in the red from the experiment, and spheral is in the blue. And in experiment, you can only pick up so many fragments afterwards. So there's not as many data points as there are from the hydrocode, but by adjusting the damage model parameters, you can find a pretty good match to the experiment. And that helps improve our simulation for materials that we might not have as much knowledge about. We need to make sure for the basics, for homogeneous granite-like or basalt-like materials, that we can match well between experiment and code. An example of a recent tri-lab effort that's ongoing still. We've been working with Goddard Space Flight Center, Los Alamos, and Sandia over the last 5 or 6 years, a little over 6 years now, I think, are these very detailed end-to-end case studies. The first one we looked at was asteroid Bennu, which was really of interest because Bennu has a small chance of impacting Earth in the late 2100s, something like a 0.037% impact probability. And it comes really close to the Earth every 6 years. So we have a lot of detailed information about it. And it's really big. It's about 500 meters across. So it's at the size range where it turns out, and we studied this pretty carefully in the 2 papers we published on this topic, that a kinetic impactor really couldn't handle something like Bennu, even with 25 years warning time and multiple launches and optimizing for the best possible mission trajectories to get as much mass and velocity on it as possible. Even assuming you have the SLS rocket available, you just can't deflect it with many kinetic impactors. So you really need to take a nuclear device approach to prevent it from impacting the Earth. And we did several different kinds of code comparisons, both kinetic impacts and nuclear explosions, with our collaborators at Los Alamos. That was a really interesting study to go through. And the next 2 case studies that we've looked at were looking at the DART target and also Comet Churyumov-Gerasimenko, which is a mouthful, so it's often called Comet CG. That was the target of the Rosetta mission that was the first Comet lander mission, and very successful a few years back. If you followed that in the news, we scaled it down somewhat because Comet CG is very big, to make it a size where it'd be more typical threat for the Earth from an asteroid or something that's more in that range where there's more uncertainty about which ones could impact in the future. But this is a very bilobate shape. A lot of people call it a rubber ducky shape. And so that was a really interesting scenario to look at for shape effects. And just to summarize everything we've talked about, asteroid impacts represent a national security threat, and they require advanced science and technology solutions, which is why we think a lot about them in our group and how to help out. And while asteroid impacts are fairly low probability, they are a very high consequence risk. So it does merit doing the homework ahead of time to be ready if there is a real emergency, to be able to give policymakers information so they can make risk-informed decisions. And surveys of near-Earth objects currently, there's many potential threats that remain undiscovered. So there's a lot of work in that realm going on. And our options for impending impacts include taking the hit, pushing the asteroid out of orbit, staging a deflection, or breaking the asteroid apart. the techniques that we model for deflecting or disrupting our nuclear energy deposition and kinetic impactor. Then I have some images on the right here to emphasize the role that NASA and other international missions are playing in our understanding of asteroid material properties. So we work closely with these partners on future mission technology and mitigation simulations to help us prepare for any future threats. So that's about it. I'm happy to take some questions.
Great. Let's thank our speaker. Okay, I had a surprise for you. And there were a couple of questions in the Q&A. So Megan, Reed Ginoza asked about the typical material composition of asteroids. Maybe you could expand on what the population's like out there.
Sure. So they're pretty diverse in terms of composition. They're mostly SiO2. They're mostly Earth-like materials, but then there's a lot of higher Z materials mixed in. So for nuclear energy deposition, for example, we care a lot about how much iron is in near the surface, or other higher Z materials will affect how the energy from X-rays is deposited near the surface. So we have pretty extensive meteorite collections that sample a lot of different types of asteroids, and then people map those into different asteroid classes. But we think there's a bias effect, and that some of the weaker, more primitive asteroids are undersampled in the collection. So something like Ryugu or Bennu that's tends to be more volatile rich, more primitive, a little bit weaker. Those tend to not be as well represented. So we have meteorites like Allende that have similar composition to that, but it's a challenging problem to try to understand the diversity. And that's a lot of what Mary Berkey has been doing recently with her energy deposition calculations, is looking at that sensitivity to those different types of asteroids. So they're categorized by C type. So Ryugu it stands for carbonaceous type, although they don't typically have that much carbon in them. It's just that they tend to have a little bit more volatiles and other things. Ryugu and Bennu are both C type. S type, I think Itokawa is an S type, so that's a little bit more common. A typical ordinary chondrite type asteroid. So yeah, there's people that make their whole career studying the details of the composition of these, so they're pretty wildly varying. But then also the structure, the porosity, in some ways an even more interesting aspect. That they can vary a lot in terms of what that porosity near the surface or in the subsurface looks like. And we definitely need more information from future missions about what the internal structure of these look like.
Great, thank you. Shervin would like to know if existing defense systems are capable of providing any protection against near-Earth objects.
Let's see. Let me look at the question again. Oh, no. And so that's a good question to clarify, that anything that's reachable by an ICBM would not be something we would be staging. If we stage a deflection or disruption, it would be astronomical distances from the Earth. It wouldn't be, a low Earth orbit, anywhere close to the Earth. So that wouldn't be something we would use. If we didn't have time to deflect it far away, deflect or disrupt far away from the Earth, the best we could hope for would be emergency response. So evacuating people from the affected area and securing infrastructure. And something as small as Chelyabinsk, even just instructing people to stay away from windows would still help prevent a lot of injuries. So there's some things we can do.
Okay, thank you. The next question is, do we have an idea of how many potential threats might be undiscovered?
Yeah, I think if I go back to one of my earlier slides here, sorry. It's probably in the hundreds of thousands here. If you see the gap between number of asteroids at the Tunguska scale, about, a little under 100 meters in diameter. We've only discovered maybe, looks like 1,000 or so in that range. We discover about, or I should say the community at large discovers about 2,000 new near-Earth objects every year. So that it is, proceeding at a nice pace, but there's just such a huge gap that there's a lot of work to be done by telescopes like the Vera Rubin Observatory in Chile is going to come on board in a few years. That will do a lot of important work. And also NEOSM, when that launches, that will do a lot of important work. And follow-up observations are really important. So it's not just enough to discover it, but then to really narrow down its orbital path to know whether or not it's impacting Earth, when it would impact Earth. That requires a lot of follow-up by other telescopes. So it's really in the hundreds of thousands range for things that could do significant damage.
Great. Shervin would like to know if the SPH code used for breakup analysis is available outside Livermore, and how does it couple with trajectory and aerothermal analysis?
Yes, so Spheral is on GitHub, so anyone can download it. It's open source, and encourage people to do that. We have a lot of collaborators externally that use Spheral for that reason. And then the second part of the question was, trajectory and aerothermal analysis. I'm not totally sure how to answer that. If by trajectory, I'm gonna assume for that you mean if we do a disruption and then we want to calculate the trajectory over longer time scales, you could keep that simulation running in Spheral and then just turn off the hydrocode part of it, turn off the shock physics, and just have n-body gravity on, and carry that out over much longer time scale. So that is a really nice feature of Spheral. We have a grad student, he finished his PhD a little over a year ago, that the focus of one of his chapters was doing that work and seeing for disruption calculations what is a statistical representation of the dispersion of fragments from these events, and how to calculate that over, assuming different types of initial asteroid orbits. And that was really interesting. I think that's going to be published very soon, actually. And for the aerothermal, assuming you mean the atmospheric entry calculations, that's rapidly evolving. Jason Pearl is doing a lot of new algorithm development for that. So I'm probably not the best person to answer that, but Mike Owen or Jason would give a better answer on the latest there.
Okay. We're getting close to the end of our time. There are two more questions, if we can maybe just get these last two. The first is a follow-up. How do you measure the porosity of the surface? And the second is, how much advance notice do we need to begin mitigation efforts?
So the porosity at the surface is a tough one. We don't have a lot of direct information on that, other than we have bulk density estimates of asteroids, and from those, comparing to the grain density of the minerals at the asteroids, we know that they must have a certain amount of total porosity. And how that porosity is distributed is kind of an open question. It could be, it's a combination of macro and micro porosity. So that's why it's important to do these scans of different possible material properties, different ways of distributing that porosity between boulders and gaps between the boulders, and the matrix material that has the porosity at the grain scale. But we would love to have more information from landers and in situ experiments at asteroids to get at that question. And so I think that's something that'll be a big push for the next generation of planetary defense missions, is getting at that information a little bit better. And for the other was the length of time to be able, that you would need, let's see, how much time prior to impact would we know the, oh, okay. Yeah, so this is, if we didn't, even if we didn't know the Earth impact location exactly, some work on mitigation would probably begin, and we model that at the Planetary Defense conferences. Even before you know which country it's going to hit, you still want to prevent it from impacting. And as the asteroid gets closer in these scenarios, often the observatories are able to nail down, okay, oh, it's actually going to impact in this part of China or in this part of Africa or this part of the United States. But flying a reconnaissance mission ahead of time to an asteroid is another way of nailing down the impact location earlier. So that we've also looked at scenario studies doing that as well. And that's an important, being able to have rapid response missions is really important. But you know, you don't have that much time. If you want to do a deflection and not have to do a disruption, you ideally want 10 years or more. So you don't want to wait too long before you start getting something out there to stage a deflection. Otherwise, you run out of options. So it's a pretty complicated array of things to consider. And so that's why we do a lot of modeling of real scenarios based on real asteroid orbits and something that could impact in the future.
Great. Thank you, Megan, for coming and talking to us today. And thank you to you and our audience for bearing with the technical difficulties that we had at the beginning. Next month, of course, we'll have another one of these seminars. We hope to see all of you there and invite some friends, please. And also, please remember to vote. So everybody, if you can clap or send a chat or what have you. Thank you, Megan, again.
Thank you.